So the overall power available from a wind turbine is defined by this equation, which I have posted derivations for. But let's take a deep dive and look at what this means. So there's a factor of 1/2 in front, which you can see from the derivation. So the power equals 1/2, and then we have density is a factor, area is a factor, coefficient of power is a factor, and velocity is cubed. So this is really important about how velocity is cubed. So let's look at each of these. Let's look at density. Density, the equation for density from ideal gas laws is pressure over R, ideal gas constant, and T for temperature. So here we can see as pressure increases, density will increase. And if density increases, then power will increase. Therefore, increase of power. And when does pressure increase? Pressure increases at the bottom of a column of fluid. So pressure increases lower. So what this is saying, if we just look at density, you would conclude that you want wind turbines to be as low as possible to the ground to increase pressure, but therefore you find a higher density, therefore you find a higher power. But that is not true because of this factor. Velocity is cubed. So velocity cubed, that's huge. A cubed root of the velocity, and the velocity we're talking about here is wind speed. So this is literally, if we have a wind turbine, it works by the wind hitting it. So it's literally the velocity v of the wind hitting those blades that are making that angular rotation happen, giving us the power value in watts, which we will be able to investigate. So with wind speed being cubed, and it is windier up high. So wind speed increases with elevation. So don't be fooled by density decreasing with elevation. Wind speed increases with elevation. Therefore, you want your wind turbines taller, means higher power output. So let's look at another factor. Oh, if we look at our density again, density is also related to temperature. Temperature is on the denominator. Since it's on the denominator, if it gets smaller, so temperature decreases, then density will increase, means more power. So that's the effect of temperature on a wind turbine we can see there. Let's talk about this term area. Area A. The area is the swept area of the wind turbine. So if you take these 3 blades and you rotate them, then this is the area we're talking about in that equation, where if you were to take this value, this would be radius of the area that I just drew there, so that's what area means. The last part of this equation is CP, coefficient of performance. So this is not called the Betz constant or the Betz limit. The Betz law makes a limit. So the Betz limit is equal to 0.59. So again, this is not always 0.59. It's just physics limits this to 0.59. So that's theoretically as big as this number could get. If it's coefficient of performance higher is better. But if you look at the derivation of the Betz limit, it'll show you that physics governs this. So basically, coefficient of performance is it's like a catch-all constant that mathematically describes, you know, the friction and things like that, and how we can get to a like efficiency limitations in creating power out of the velocity that is given to us over this cross-sectional area at a certain density. So it's not always 0.59. That's rare. Around right now, 0.4 to 0.45 are more realistic. But physics says that you can never possibly go over 0.59. So it's sort of a losses kind of constant, but be aware that there are other losses in a wind turbine as well. So this Betz limit does not take into account all of your frictional losses in your gearbox and things like that, all the loss due to heat in the mechanical devices, etc. So it's a sort of a physics catch-all kind of loss. So there you have it. This is the overall power available from wind, and area will be the same, coefficient of performance will be the same. What will change in your situations that you're looking at is velocity. So it's going to be important next week to take a look at, well, what are the velocity profiles in different scenarios, and where could you put wind turbines in order to maximize the power that you can capture from the wind.